So here's our problem. At the beginning of an experiment, there's 372 grams of radioactive matter, and after 195 minutes, there's only 23.25 grams. So we need to figure out three things. Part A, what is the matter's half-life in minutes? Part B, to find a formula for G of T, the amount of matter remaining at time T. And C, how many grams will be left after 29 minutes? So we start with part A. We need to figure out the half-life, meaning how long it will take for the amount to get from 372 to 186. But before we can do that, we need to find the decay rate before the half-life, so we have to set up the equation and identify the variables. The equation here is G of T is G sub 0 times e to the power of negative r times t. G of T is the amount after elapsed time, which in this case is 23.25. G sub 0 is the initial amount, which is 372. E is a mathematical constant used in exponential and logarithmic equations. R is the decay rate we're trying to figure out, and T is the elapsed time, which is 195 minutes. So altogether, this equation should look like 23.25 equals 372e to the power of negative r times 195, as you can see right here. Because we're working with the variable e, a graphing calculator might be necessary to get the exact right amount, but we could express it logarithmically first using what we know to solve for r. So here we have our equation, right there again. So we have to divide both sides by 372 to simplify that right side. Now we have 23.25 over 372 equals e to the power of negative r times 195. Our next step is to simplify the fraction on the left side. For this, you might actually need a calculator. And together, you get 0.0625 equals e to the power of negative r times 195. So now we have to rewrite this to apply the exponential rules. So we have this natural log of 0.0625 that equals negative r times 195. The last thing we have to do to solve for r is to divide both sides by 195 and switch signs. As you can see, r is negative, we have to make it positive. And together we should get r equals negative natural log of 0.0625 over 195. On our calculator in decimal form, this is r is approximately 0.01421. That's our decay rate. So now that we know the decay rate, we'll rewrite the problem so that G of T is half of G sub 0, the initial amount. And this time we're solving for time instead of rate. So because 186 is half of our initial amount, it's going to be 186 equals 372e to the power of the rate we just made times t. Now for some of this equation, let's replace the ratio with the term r for simplicity, and then we'll add it back in. So our first thing to do is to divide both sides by the initial amount, as we did in the previous step. And that gives us 1/2 equals e to the power of r times t. Now the reason we get 1/2 on the left is because on the left side, we are dividing 186 by 372, which is 1/2. Our next step is to rewrite and apply exponent rules so that we get natural log of 1/2 is r times t. So then we solve for t, and this time we do need to bring the rate back. So this time we get t equals negative 195 natural log of 2 over natural log of 0.0625. And if we use our calculator to get the half-life in minutes, about 48.75 is what we get. So it's approximately 48 minutes and 45 seconds for the half-life. Parts B and C are going to be easier now that we've done part A. So we just have to rewrite the formula to solve for G of T, the amount after elapsed time. So we can write this as G of T is our initial amount, 372, times e to the power of approximately our rate times our given time. And as you can see, I put the rate in decimal form. It is approximately negative 0.0142. Now we can use this formula to solve the final part of this question in part C. How much matter will remain after 29 minutes? In this case, we can just replace t in the above formula with 29. And that's why we get G of T equals 372e to the power of approximately negative 0.0142 times 29. Now at this point, you'll need a calculator to determine the amount, but you already have the formula. And if you want to be more accurate, you can rewrite the rate in log form, as I've done here, instead of the decimal. But this brings our amount, after 29 minutes, to approximately 246.3 grams. Just to confirm everything, I wanted to log the equation in Desmos, our graphing calculator. As you can see, I have here 372e to the power of our rate times x, and x is going to equal time because x values on the graph will equal time, whereas the y values will equal the amount. As you can see right here, at 372, the time is at 0, and the amount is at 372. Now let's determine the half-life at 186. It's going to be around 48. As I mentioned before. Now we need to figure out the amount of time after 29 minutes, which is around here. It is approximately 246.3, as I said before. So this graph appears to be correct.